Let's talk about a concept called isomorphism. So isomorphism is about two graphs G1 comma G2, let's say, and we say that two graphs are isomorphic if they have same adjacency. Adjacency in the means connectivity. Example, let's say take two graphs like this A B C D, and let's draw a cycle like this. Then G2 1 2 3 4. So 1 to 4, 4 to 2, 2 to 3, 3 to 1. So if you see these two graphs, apart from labels, okay, don't worry about labels. Structure wise, they have same structure. Here, there are four vertices, you have four vertices, and every vertex is connected to two other nodes. Here also every vertex is connected to other two nodes, and not more, apart from that, every vertex, example, if you have a vertex A, in the same way we have vertex 1, that means whatever vertex A is doing, example vertex A is adjacent to two vertices, right? In the same way this vertex also adjacent to two vertices. Okay, so then we say that these two graphs are isomorphic. So to say two graphs are isomorphic, the adjacency, so let me say the adjacency between these two should be same, like whatever the adjacency they have, this graph also should have same adjacency. Adjacency means the connections, like whatever the connection this graph has, same connections this graph should have. So informally I can say like this graph somehow by adjusting the edges, like example, if you redraw this graph without losing the relationships, and if you get this kind of structure, then we say two graphs are isomorphic. Example, what I do is I redraw the graph 1 to 4 I write first, then 4 to 2 I write, then 2 to 3 I write, so I am not losing any adjacency. So 3 to 1 if I draw, then same graph I got, right? So then these two graphs are called isomorphic. So this is informal idea about isomorphism. So far whatever I told you, it is informal idea about isomorphism. Then what is formal definition of isomorphism? We'll see. Two graphs are G1 and G2, let's say, with vertices V1 E1 V2 E2 are isomorphic if there is bijection. You know what is bijection, right? One to one correspondence. Usually bijection is nothing but, example, there are two sets like 1 to 3 ABC. Bijection is nothing but this kind of mapping. So you know that. So if you don't know, then please go through functions lecture first, after that you come to this this lecture. In functions I taught what is bijection. Now there should be a bijection from one set to another set, and what is the domain and codomain? From vertices of G1 to vertices of G2. So we have taken two graphs, right? Every graph has vertex set. Then vertices of graph 1 and vertices of graph 2, if I take as domain and codomain, let's say V1, V2, there should be a one-to-one function. And that function should satisfy this condition. What is that? For all vertices u and v in G1, whatever the two vertices you take in G1 graph, then if that u comma v is an edge in graph number 1, then that should happen if and only if f of u, f of v belongs to belongs to edge set of graph 2. That means, example, 1 2 3 are vertices of, let's say, graph 1, ABC are vertices of graph 2. Then example, in your graph G1, I am showing for just example, there is an edge from 1 to 2. Okay, then this is, let's say, graph G2. Now what is, according to this mapping, what is f of 1? F of 1 is A, f of 2 is B. Then according to the definition, if really two graphs are isomorphic, f of 1 and f of 2 should belongs to edge set of the graph 2. That means f of 1, let's say here A, f of 2 is B, between A comma B there should be an edge. Similarly, if there is, the if and only if means, if this is true, this is true. If this is false, this should be false. That means if there is no edge between u comma v in graph number 1, then in G2 also there should not be an edge. That is what if and only if. So that means if there is no edge between 1 comma 2, then A comma B also should not have an edge. What is the significance of A and B here? Where A is the image of 1, B is the image of 2. But how to decide that one's image is A, two's image is B? So this definition won't say that how to calculate the images, but finally you should show such function. Okay, so you should map it. It's your responsibility. Isomorphism says that you should show such function such a way that adjacency should be preserved. Whatever I explained here is called adjacency. That means if you can show this kind of function where whenever 1 and 2 are connected, a comma b should be connected. Whenever 2 3 let's say are not connected, b comma c should not be connected. Such a function if you show, then we say that two graphs are isomorphic. Okay, but how to get that function is up to you. Okay, now what is the difficulty in this isomorphism? I will tell you why isomorphism is a difficult problem is, let's say you don't have any clue how to map the elements. Okay, let's see this scenario. Example, you have n vertices v1 v2 v3 so on vn in graph number 1. Okay, in graph number 2 you have u1 u2 let's say un vertices. Okay, n vertices. If number of vertices equal, then only we can have bijection. Now the question whether two graphs are isomorphic or not, if you want to know, then you should show one bijection, right? But I don't know how to map that bijection, like should I map v1 to u1 or v1 to u2, so on. So anything is possible, but there should be some bijection. Now if I use some mathematics here, there are n factorial bijections. Okay, then in the worst case what you should do is take every possible bijection and check whether that bijection is satisfying this condition. What is that condition? Preserving the adjacency. Since there are n factorial bijections, any bijection might satisfy this condition. Don't check only one bijection and don't say two graphs are isomorphic or not isomorphic. To really check whether two graphs are isomorphic or not, in the worst case, every function, bijection function you have to calculate, and for every bijection adjacency should be checked. So let me show this idea with 3 vertices. Example, if you have 3 vertices in G1, they are ABC, and in G2 you have let's say DEF. Okay, now the question whether these two graphs are isomorphic or not, then one brute force method is, like currently we don't have best methods, so we have to use only brute force method, that is like map A to D, B to E, C to F. But it may not be true, right? This may not be the ultimate idea. There are some other possibilities like mapping A to E, B to D. Even that also we have to check. That is what I am saying. So form one way of function, then check whether adjacency is preserved or not. How to check adjacency? Check edge between A to B in graph number 1. If there is a edge, then check between D comma E in G2. Then mark it like in that way. If there is edge here, there should be an edge here. And observe B comma C combination. If there is edge here, there should be edge between EF. In that way, for all the edges of graph G1, check the edges and there should be corresponding edges in G2 between the corresponding vertices. What if it won't happen? Then this bijection is wrong. It doesn't mean that two graphs are not isomorphic. Maybe another combination will work. Okay, so check one more bijection. Take one more bijection where map A to E, B to D, C to F, and again check the adjacency, like take AB and observe adjacency in G1. If AB are connected in G1, go to G2 and check between D comma E. This thing we should do for every combination of vertices. Okay, then if you somehow, so sometimes what happens is you have, let's say you calculated one bijection, then for this bijection you observe the adjacency and that adjacency is preserved. So if that adjacency is preserved, then we say that two graphs are isomorphic. But that is best case. In the worst case, what happens? Whatever the bijection you try, you might fail. Then what happens? Then in the worst case, n factorial bijections you have to evaluate. It takes lot of time. Okay, so that's why isomorphism is a difficult problem. Okay, in the worst case, lot of evaluations we should do. Now let's come to discrete mathematics. In discrete mathematics area, how we saw, see this problem is like isomorphism is. So what is isomorphism? One we learn. Second one, given two graphs, how to check that two graphs are isomorphic. That's enough. So in GATE exam, especially from discrete mathematics, they ask Only one question. They give you graphs and they ask whether that graphs are isomorphic or not. Then how you check it? Already I told you. So it is very difficult to map the elements. Like if they give a graph with 10 vertices and one more graph with 10 vertices, we don't know how to map them. Like which vertex to be mapped to which vertex, we don't have idea, isn't it? Then how to do it? I will tell you. There are some heuristics. Otherwise some observations. If you follow that observations, we can do it. How I will tell you. First thing, example, you have a graph with 3 vertices and there is a graph with 3 vertices, but it is like this, and second one is like this. Then definitely these two graphs are not isomorphic because you can't get mapping. Why? Because really these two are having same structure. If there is no cycle here but here there is a cycle, then how they will be same structures? No, right? Structure wise they are different. So whatever you do this graph, like whatever the way you adjust, you never get it back. That means this cycle will decide that these two graphs are not isomorphic. So isomorphic means the structure of the graph should be same. Understand? So in that way, easily we can check whether two graphs are isomorphic or not. For that, there are some important properties. I will explain them. So we'll see now properties for two graphs to be isomorphic. So we know that if number of vertices doesn't match, then how can you show the one-to-one correspondence? No, right? That's why number of vertices should be same. Okay, let me list out all possibilities. To say that two graphs are isomorphic, one necessary condition is number of vertices should be same. Okay, number of vertices. What about number of edges? So we know that it's a adjacency, like two graphs should have same structure. For that, number of edges also should be same. So I say number of edges also should be same. If number of edges are not same, let's say, then two graphs are not isomorphic. Second one, it is necessary condition. If number of edges are same, it doesn't mean that structure is same, right? Sometimes what happens, you can draw a graph, two graphs with same number of edges, but in a different structure, right? See, different adjacency. That's why be careful. Number of edges is necessary condition. You should satisfy. If you violate, graphs are not isomorphic. If you satisfy, still graphs may be isomorphic, may not be. So all the conditions whatever I am giving are just necessary conditions, may not be sufficient. Okay, there is no sufficient condition generally. Now number of vertices, number of edges, and sufficient condition is only the definition. What is that? You should show one-to-one correspondence. But I don't want to do that because it is computationally expensive. I don't do that. So I try to find out shortcuts. That shortcuts, check the number of vertices, then number of edges, then check degree sequence. This is one more property of a graph, right? So degree sequence of two graphs should be same, otherwise they are not isomorphic. Again, it is not sufficient. Sometimes there may be graphs with same degree sequence, but again they are different. So that's why go to one more parameter. This is very important parameter. Most of the time it will work. That is, number of cycles. Okay. So just observe the number of cycles and different types of cycles. Check the number of cycles and length of the cycles. I can say length of the cycles like this. Okay. Second one with 5 vertices, let me draw in different way. 1, 2, 3, 4, 5 like this. They give like this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And are they same? Are they isomorphic? See, there is a triangle. Here there is no triangle. Don't say that this is triangle because this is not a vertex, right? So here there is a triangle with 3 vertices, but there is no triangle with 3 vertices because this is just crossing point, not a vertex. Okay. Then can you show any triangle in this graph with 3 vertices? No. Then these two graphs are not isomorphic. So easily we can check it. So I will give you a lot of examples to check whether two graphs are isomorphic or not. But observe the properties. One more property you can see, like degree sequence, maximum degree, minimum degree. Okay. You can also identify maximum degree and minimum degree, this kind of things. Then sixth property. So there are so many hundreds of such properties. I'm just giving very important properties. Observe the adjacency of some peculiar, otherwise particular vertices. Example, in your graph, observe adjacency of, I can say adjacency of peculiar. Okay, peculiar vertex. That means a special vertex. Like example, if your graph has a vertex with degree 6, but there is only one such vertex. Observe its adjacency. Like example, there is one degree 6 vertex which is connected to like degree 2, degree 2, degree 3. In another graph, there is a degree 6 vertex. There is only one, and that is connected to degree 2, degree 3, degree 3, then definitely these two are different structures. Really these two graphs are same. This vertex behavior should be same. What is the behavior of this vertex? It is connected to three vertices where one vertex degrees 2, another vertex degree 2, another vertex degree 3. But here it is connected to degree 2 vertex and degree 3 degree 3. How they are same, right? They are not equal. In that way we can check. Understand? Now we'll see some examples of isomorphic graphs. In the GATE exam they give you this kind of graphs. Are they isomorphic is the question. So if you want to number them, you can number them like 1, 2, 3, 4, 5, 6, 7, 8. This is 1, 2, 3, 4, 5, 6, 7, 8. Just randomly I numbered them. Now you see, first focus on number of vertices, same. Then check the number of edges. You will realize that number of edges also same. Okay, otherwise you count it. How to count number of edges? I will tell you one easy technique. Sum of the degrees theorem. Apply the sum of the degrees. For that I am listing out all the degrees. Degree 2, 1, 2, 3, 4. Degree 4. This is degree 2, degree 2, degree 2. 1, 2, 3, 4. Degree 4. And this is degree 2, this is 1, 2, 3, 4, degree 4. Apply sum of the degrees 4, 6, 10, 12, 14, 16, 20, 22. So 22 is nothing but twice the number of edges. 2 into E equal to 22, E equal to 11, right? So number of edges in this graph is 11. In that way you can compute. So why I did this one rather than counting directly is so that you can list out all the degrees also. Okay, let me list out all the degrees here. Degree 3, this is degree 3, degree 1, 2, 3, this is degree 2, 1, 2, 3, degree 3, degree 2, degree 3, degree 3, right? Just list out all the degree sequence here. This is 2, 2, 2, and there are some 4s also, right? Like 2, 2, 2, then one more 2, 4 2s, and 3 4s, right? So 12, 14, 16, 18, 8 plus 20, one more 1, 2, 3, 4, 5 vertices of degree 2, okay? 5 plus 3, 8. Here degrees are, there are 2 degree 2 vertices and 1, 2, 3, 4, 5 vertices of degree 3. 6 vertices, sorry, then 3, 6, 18, 20, 22. Sum of the degrees is 22. 22 equal to twice the number of edges, then number of edges should be 11. Yes, number of edges are matching. Sir, why are you counting number of edges in so difficult way? Why not you count like this, 1, 2? But here I observed the degree sequence also, right? So if you see the degree sequence, it is 2, 2, 2, 2. Here it is 2, 2, but followed by 3, 3, 3, 3. When degree sequence is different, then graphs cannot be isomorphic. That's why these two graphs are not isomorphic. I will tell you one more reason why these two graphs are not isomorphic. See the triangles. There is one triangle here, 2, 3. There are 3 triangles, isn't it? But in this graph, I am seeing only 2 triangles. So number of triangles also should match. That's why these two graphs are not isomorphic. Okay. So from now onwards, when two graphs are given, check all these properties, whatever you like in some order. Okay. Generally start with number of vertices, after that number of edges, then followed by degree sequence. If degree sequence also matches, then go for number of cycles and cycle lengths. Two graphs, whether they are isomorphic or not, we'll see. So first we start with number of vertices, 5 and 5. Second, number of edges. So let me list out degree sequence first, so that I can compute edges also, right? So I am listing out degree sequence. Degree 3, right? Degree 3, degree 3. This is degree 2, degree 3. So here degree 3, degree 2, degree 3, degree 3 and degree 3. Now degree sequence matches, right? Whenever degree sequence matches, then I can say that number of edges also will be definitely same, because according to sum of the degrees theorem, sum of the degrees here and here same, but we know that sum of the degrees actually 2 into e, right? Because 2 into e values are same, then 2 will get cancelled. Okay, let's say it is number of edges here e1, number of edges e2, then sum of the degrees is 2 into e1 here, sum of the degrees here is 2 into e2, but they are equal, right? Because degree sequence is same, then 2 will get cancelled and number of edges definitely should be same, otherwise you count them, you will understand. Now, so we have checked three things: number of vertices, number of edges, degree sequence. Then what to do? Cycles. So let's try cycles. So there is a triangle here and there is one more triangle here, right? There are two triangles I can see. Check here triangles. 1, 2. Even here there are two triangles. Let's see any four length cycle. There is one four length cycle. 1, 2, 3, 4. Any other four length cycle? Yes. 1, 2, 3, 4. There are two four length cycles. So here also we have one, second one, one more here, you see, B, D, E, A. There are two four length cycles. So whatever I am trying, so whatever the property I am trying, so both graphs are satisfying. Then what to do? Then slowly I am getting confidence that maybe these two graphs are isomorphic. So if really these two graphs are isomorphic, then we can construct one graph from another graph. That means I can redraw a graph so that that will match to another graph. So what is my confidence is, probably by redrawing one graph we can get another graph. Let's try that. So what I do is, however, degree 2, there is only single vertex of degree 2, then E should match with 2, no doubt on that. And remaining four vertices we should observe. Here there is a triangle attached to triangle, but here if you see other vertices A, B, C, D, can we make this kind of structure? We'll see. So A, D, since this E is connected to A comma D, here this 2 is connected to 1 comma 3, right? Then 1, 3 should have same behavior like A comma C. Okay. Now here 1, 3. So we have A comma, what is that one more thing? D, right? A comma D. So we have BC here. Here you have 4 and what is that one more thing? 4 and 5. So between 4 and 5 you have edge. Between B and C you have edge. Then I realize that the position of C should be like 5. Then I redraw C here. Then you will understand everything clearly. So I am removing C and I am redrawing it. So draw all the edges from C to anything. BC, then you add like this, newly constructed graph. Now AC there is an edge, redraw it. Now DC there is a edge, then redraw it. Remove this vertex C here. Okay, I am repositioning C, that's it, not more than that. So I am removing all the edges, then you get this graph. Is it not this one same, right? So that's why by redrawing this graph I got it. That's why these two graphs are isomorphic. Understand? Really you want to prove that two graphs are isomorphic, you have to reconstruct the graph like this.